is all you need. Paper analysis by Isham Rahman. Introduction. Before transformers, sequence modeling tasks like translation, summarization, and text generation mainly used recurrent neural networks such as RNNs, LSTMs, or GRUs. These models process input one step at a time, which makes them slow and hard to parallelize. When they capture sequence order, they often struggle with long-range dependencies because information fades as it passes through many steps. Attention mechanisms were introduced inside these models to help them focus on relevant parts of input sequence, but the base structure still relied on recurrence. The authors of this paper asked an important question: what if we remove recurrence and convolution completely and build a model entirely for attention? Their proposal, the transformer, does exactly that, showing the attention alone is enough to achieve state-of-art results while training much faster. Background. Earlier models tried to replace recurrence with convolution to gain speed. Architectures like BaseNet and Conv2S could run in parallel unlike RNNs, but still need many layers of convolution to connect distant words in a sentence. This made them less efficient for capturing long-term relationships. Self-attention offers a simple alternative because it directly relates every token in a sequence to every other token in a single operation. Instead of passing information step by step, the model learns pairwise dependencies in one layer. This is not only shortens the path link between distant words but also reduces the difficulty of learning context across the entire sequence. The transformer builds on this idea, eliminating recurrence and convolution altogether. Model architecture. The transformer uses an encode-decode structure, which is common framework for translation tasks. The encoder reads input sequence such as sentence in English and converts them into a set of continuous representations. The decoder then takes these representations and generates the output sequence such as the translated sentence in German or French. Unlike earlier models, both encoder and decoder in the transformers are made entirely of self-attention and feed-forward layers. There is no recurrence and no convolution. This makes the architecture highly parallelizable, allowing it to train on other modern GPUs much more efficiently. Stacking several layers of design creates a deep model capable of learning complex language patterns. Encoder and decoder stacks. The encoder is built with 6 identical layers. Each layer has 2 main parts: a multi-headed self-attention mechanism that lets every word look at every other word, and a position-wise feed-forward network that transforms each position separately. Both parts include residual connections and layer normalization for stability. The decoder also has 6 layers with 1 extra attention block. These attention blocks allows the decoder to focus on encoder outputs while predicting the next word. Another important detail is that the decoder marks future tokens so that it cannot cheat by looking ahead. This ensures the predictions depend only on past and present information, like in real text generation. Attention mechanism. The attention mechanism, the core of the transformer, is its attention mechanism. In a scale dot production, each word has a query, a key, and a key value vector. The model calculates attention scores by taking dot product between a query, all keys, scaling them by the dimension of the key, and applying softmax. These scores are then used to weight the values, producing a weighted sum that represents the context for that word. Multi-headed attention repeats this process in parallel several times with different learned projections. Each head can capture a different type of relationship, such as focusing on nearby words, matching subject-verb parallels, or aligning translations. The outputs of all heads are connected and project back, giving this model shared representation than a single attention mechanism could. Feed-forward embedding and position embedding. In addition to attention, each layer has feed-forward network applied independently to each position. This gives the model more nonlinearity and capacity to process information. Input words are first converted into embeddings, which are vector representation. To share information between input and output layers, the same weight matrix is used for embeddings and the softmax output. Since transformers do not have recurrence or convolution, they cannot naturally capture order in sequence. To solve this, the author adds positional encodings to the embeddings. They use sine and cosine functions of different frequencies, which allows the model to represent positions uniquely. These encodings also have nice mathematical properties, letting the model generalize to longer sequences than it was trained on. Why self-attention? The paper highlights several reasons why self-attention is a better choice than recurrence or convolution. First, it has shorter path length between any two tokens, which RNN's information must pass through many steps to connect distant tokens, but in self-attention the connection is direct in a single layer. Second, self-attention is highly parallelizable because all the tokens in a sequence can be processed at once. Unlike RNNs, they are inherently sequential. Third, a computational complexity is lower than recurrence when the sequence length is smaller than hidden dimension, making it more efficient in many practical tasks. Another benefit is interpretability. Attention weights can be visualized to see which words the model focuses on, providing insights into how it makes decisions. Training. The author trained their transformer models on two large translation datasets, WMT 2014 English to German, which is about 4.5 million sentences pairs, and WMT 2014 English to French, which is about 36 million pairs. Training was done on 8 P100 NVIDIA GPUs with batches of around 25 tokens. They used Adam optimizer with special learning rate schedule. The learning rate increases during warm-up phase and then decays proportional to the inverse square root of the step number. The dropout used to prevent overfitting, and level smoothing was applied to improve generalization. These careful training choices were important for making the transformer convergence effectively and achieve stronger results. The transformer achieved impressive results, outperforming our previous models on machine translation benchmarks. On English to German task, it achieved a blue score of 28.4, which was more than 2 points higher than the previous best. On English to French task, it scored 41.8 blue, again setting a state-of-art score, which made this more exciting than it is trained much faster than RNN or CNN based models thanks to its parallel design. Beyond translation, the authors also tested the model on English phrasing tasks where it performed competitively, showing that the architecture generalizes well beyond translations. These results confirm that attention-only models can not only match but surpass traditional sequence models. Conclusion: the paper concludes that the transformer is the first sequence model based entirely on attention without recurrence on convolution, and it brings clear advantages. It is faster to train, scales better with data and model size, and delivers higher accuracy. This simple yet powerful idea had a massive impact, laying the foundation for modern NLP models like BERT, GPT, and many others. The authors also suggested that attention-based models could be applied beyond text areas like vision, audio, and video. Today we know that this vision came true as transformers have expanded into nearly every area of AI. This paper truly marked a turning point in machine learning research. Thank you.